The fourth dimension. For a long time now, the idea of a fourth dimension has hovered at the edge of science and science fiction, a concept so elusive and mysterious that many of us find it almost impossible to comprehend. But could an additional layer of spatial reality truly exist, hidden beyond our three-dimensional worldview? Maybe, just maybe, the fourth dimension is more than a sci-fi buzzword. Tantalisingly, scientists now claim to have built a fourth dimension of space, and in this video, we're going to peer inside and explore this new reality and explain just what a four-dimensional world might look like. We experience the world as three dimensions of space and one of time, with time normally being referred to as the fourth dimension. But forget what you have learned. Today, we're going to explore an even more abstract idea. Can we build a fourth dimension of space? And what strange properties might it contain? Mathematically, at least, we can easily conceive of worlds that contain 4, 6, even 100 spatial dimensions. In fact, branches of theoretical physics, such as brane cosmology, already suggest the existence of many spatial dimensions. Remember the movie Interstellar? Now, spoiler alert here for anyone who still needs that. The wormhole that brings the crew to Gargantua moves through a hyperspace known as bulk space, which is a higher spatial dimension, and it's what allows the ship to emerge at a new non-linear location. And leaning on that other mainstay of sci-fi movies, the Marvel Cinematic Universe, the term tesseract describes a mystical and powerful cube that possesses a space stone, a device that has the ability to open portals to any location in the universe. Again, it does this by accessing a higher spatial dimension similar to Interstellar's bulk space. But the term tesseract, well, that's borrowed from mathematics, where the word describes a four-dimensional cube, also known as a hypercube. But outside the realm of sci-fi, how can we possibly conceive of something that exists in a fourth dimension? In recent years, a new generation of quantum physicists have turned that abstract question into something surprisingly concrete. Instead of searching for hidden dimensions out there, they have started to engineer extra dimensions in here. Well, in quantum labs, to be precise. It has profound implications for our understanding of reality, and it may drive quantum technological innovation well into the future, just as soon as we can grasp it. To better understand what it all means, we're first going to have to get our heads around dimensions. So up, down, left, right, forward, and back. We assume that that's all there is because that's all we can see and touch. And it may be, though, that our limited senses are constraining our understanding of reality. Imagine being born into a room with no windows. How would you ever conceive of the world beyond your immediate environment? In the 19th century British novel Flatland, the characters are all two-dimensional shapes living on an infinite sheet of paper. Our narrator, a square shape, helpfully named A Square, can move left, right, forward, and back. But he has no concept of up. When a sphere from a three-dimensional world passes through Flatland, A Square never sees the sphere. Instead, he only sees the parts that interact with the 2D world. At first he sees a point, then a growing circle, then a shrinking circle, and finally nothing at all. To our character, the sphere only manifests on two-dimensional planes as a series of mysterious two-dimensional slices that change over time. The story perfectly demonstrates the bewilderment many of us feel in trying to wrap our heads around a world beyond three dimensions. Now, if there were a fourth spatial dimension, we could never see a 4D object from the outside. But that doesn't mean that we can't explore this strange idea, and in doing so, learn more about our perception of reality.
Yeah, so I think the best way to think about four dimensions is by building an analogy with the number of dimensions that we're used to, and then trying to extrapolate it.
That's Hannah Price, a theoretical quantum physicist at the University of Birmingham. When physicists like Price talk about a fourth spatial dimension, they mean something specific, an extra independent direction in which things can move. On a flat sheet of paper, there are two directions, x and y. In everyday space, there are three, x, y, and z. Add a fourth spatial dimension, and it would simply be another direction, perpendicular to all the others. We could call it q. If a square in Flatland discovered a new dimension, it would mean a new freedom of movement. And that is really exciting for physics.
And that freedom is actually really crucial when it comes to physics because it changes the way that a lot of physical laws behave. So it changes the way that gravity would work or electromagnetism would work. And the aspect that I'm really interested in is it would change the way that certain types of quantum materials would behave. Just by adding that extra direction in which your particles can move, you can realize different states of matter that you wouldn't otherwise see in the kind of the universe that we have with 3 dimensions.
In other words, higher dimensional physics acts like a blueprint, constructing a reality of which we can only perceive a part thereof. But this is where it gets exciting. By imagining our reality as in the shadow of something higher, we might be able to glimpse at this untapped, unique physics of a 4D world.
It's like the higher dimensional system is casting a shadow into the lower dimensions that exhibits many of the same features and same properties. And so by looking at that kind of the shadow of the effect, we're inferring things about the effect that would exist in higher dimensions as well.
Price is part of a new generation of scientists who believe it is possible not only to theorize about a fourth dimension, but to actively explore it through tangible experiments. The question is how? While there is no way we can physically see a fourth dimension, that doesn't mean we can't simulate its effects on our 3-dimensional space. And the answer lies in a curious discovery from the early 1980s, known as the quantum Hall effect. In the 80s, German physicist Klaus von Klitzing was working with atomically thin layers of very cold semiconductors, effectively creating a 2-dimensional sheet of electrons. When placed in strong magnetic fields, the electrons started moving in ways that challenge our understanding of the physical world, as if slipping through a sort of secret passageway, or, more to the point, a hidden coordinate beyond what was available to them. Von Klitzing later won a Nobel Prize in physics for his quantum Hall findings. So what was going on? In these systems, the electrons were confined so tightly that they were only free to move in 2 directions, a bit like our friend in Flatland. But this is where it gets strange and a bit complicated, so stick with me. If you apply a magnetic field to this atomically thin 2-dimensional electron wafer, it makes all the electrons inside it want to move in tiny circles, except at the edges where there isn't enough space. Here, the electrons' trajectories are chopped off into semicircles. But instead of stopping in their tracks, these electrons zip along the edge, forming a conducting periphery. This is called the quantum Hall effect, and it creates a material that is electrically insulating in the middle, but conducting on the sides. This unusual duality depends on the 1-dimensional edge using the presence of a higher dimension that it wasn't expected to have access to. To understand how this works, imagine a 1-dimensional line with electrons sitting on it. If you apply a magnetic field to this, the electrons can't move in circles, as that isn't possible in 1 dimension, so they remain fixed in place. If this line is the edge of a wafer, however, the electrons can skip through the 2-dimensional plane.
Your particle is trying to move in a circle, but it keeps hitting the boundary before it's managed to go all of the way around. And every time it hits the boundary, it reflects off and it comes back in the same direction it originally started. And then it does another little circle. And this leads to what we call a skipping orbit.
In short, the electron is skipping between the exterior 1-dimensional edge and the interior insulating bulk via a 2nd dimension. The quantum Hall effect is the simplest example of what's called a topological material, a system whose behavior at the edges doesn't depend on tiny details of the material, it depends on a deeper mathematical structure underneath. And that raised an intriguing question. If a one-dimensional line can pull neat tricks when it feels the imprint of another dimension, can higher dimensions do the same? Theoretically, yes. In 2001, Xu Chengzhang and his colleague Xiangping Hu, then both at Stanford University in California, developed the mathematics that described a four-dimensional analog of the quantum Hall effect, one in which a regular three-dimensional material felt the imprint of a fourth dimension. And this idea intrigued Price.
There had been the prediction in the early 2000s of the 4D quantum Hall effect, which generalized the 2D results. And that was what really took our imagination, and we thought, okay, let's try and figure out how to realize this experimentally.
The question now was how? To create their first 4D simulation, Price and others created a lattice of atoms held in place by lasers. By tweaking the lasers, they could deform the lattice to generate the ghostly shimmer of a four-dimensional object. It was a real-world example of what a square had experienced with the sphere in Flatland. And together with a separate experiment published at the same time, it was the first realization of the quantum Hall effect in 4 dimensions. But it's hard to say what or where the 4th dimension is in these experiments. It wasn't 4D enough. Far better than conjuring the impression of a 4th dimension is actually building one, which is where we're going next. When it comes to accessing multiple dimensions, there's no better place to look than New Scientist. Our company was founded in 1956 for all those interested in scientific discovery and its social consequences. And we love to ask the big picture questions about life, the universe, and what it means to be human. If that sounds like something you like too, then why not join us? With the New Scientist digital subscription, you'll get access to all of our award-winning science and technology journalism, including our daily news, so you're up to date with the latest developments, and our deep dive features, so you're never without a captivating tale to fuel your curiosity. For a great offer on a New Scientist digital subscription, click the link in the description. So, let's build a 4th dimension. Price wanted to know if anything like it could be built in the lab. The first step was to design a model that captured the essential 4D physics in a form that experimentalists could work with. Enter Chong Yedong, a quantum researcher at Nanyang Technological University in Singapore, who, utilizing Price's theories, constructed the world's first permanent 4D electrical circuit.
So from a very pragmatic, practical sense of point of view, if our goal is to, for the first time, create a physical structure that is equivalent to a 4-dimensional lattice, making use of Hannah's principle, her model as the guiding principle, then electrical circuits are the way to go. But the advantage of using electronics is really that you can hook up different electric resonators with a wire, which means that I can take this 4-dimensional structure and I can peel it out into layers and lay it out into a 3-dimensional stack of circuit boards. If you have a 4-dimensional material, you can have a generalization of the quantum Hall effect.
To understand how it works, picture a 3-dimensional object, say a cube. If we look at this, we can see how the lines, which can be considered 1-dimensional objects, are drawn to connect elements of the shape. Now, if we unfold that cube into 2 dimensions, we get 6 squares, all spread out. Now, in 3 dimensions, we know that the edges of these squares were all next to each other, but in 2 dimensions, they're not. If we made a circuit board of this shape, we could wire it so that each edge acted like it was next to its 3D neighbor. Essentially, this is what Chong's group did. Visually, it looks like a dense, multi-layered motherboard, but mathematically, it is a four-dimensional grid. So if this circuit really behaves like a 4D quantum Hall material, how do you tell? In the 2D effect, the bulk was the insulator and the edge was the conductor acting in a special one-way state. The 4D version predicts something similar, special states that live on the 3D surface of the 4D lattice.
The whole idea behind using the electrical circuit to simulate this was to really exploit the fact that an electrical circuit you can wire up however you like. And so this means that if you want to wire it so that there are four directions in which the current can flow, you just need to attach four wires to the node of your current.
In other words, Price and Chang's teams created a three-dimensional electrical circuit whose behavior matches the equations of a four-dimensional quantum Hall material. Within its network of capacitors and inductors, there is an extra effective direction along which waves can propagate, a synthetic fourth dimension.
We were looking to show that this 4D circuit exhibited characteristics that we would expect from the 4D quantum Hall effect. And indeed, they were able to show that. So they were able to verify the existence of those four-dimensional surface states. And this was what I think the first experiment that was really a four-dimensional experiment looking at this effect, because the connectivity was four-dimensional.
Now that there was a mechanism for simulating a 4D environment, things could get really fun. By building on the basic blueprints by which Xi and Chang Yidong conducted their experiments, one could, they say, easily manifest the quantum Hall effect in 6 dimensions. Theorist Motohiko Ezawa at the University of Tokyo goes even further, saying that the kinds of electrical circuits engineered by Yidong's group have the potential to manifest as many dimensions as experimenters have the patience to wire up. All of this, however, doesn't quite prove that the universe is four-dimensional. Price herself is ambivalent to the idea, but like all good scientists, is open to discovery.
I don't know whether there are more than 3 spatial dimensions in reality. I'm not a string theorist, so I am agnostic as to whether, in fact, there are more spatial dimensions than the 3 that we experience. But I've really long been fascinated by the question of what would happen if there were. So for me, this is an exercise of the imagination and creativity.
What it does mean is that we have learned how to engineer systems that act as if they are four-dimensional. The circuit has 4D connectivity, but it still lives physically in ordinary three-dimensional space. Shinsei Ryu, a professor at Princeton, notes that each of the aforementioned experiments was conducted with a guided hand within synthetic environments. Any seeming fourth-dimensional activity was, in a literal sense, entirely of human creation. He also notes that the experiments don't account for the electrons' behaviors, such as mutual repulsion that results from their charge, which is still governed by the 3 normal dimensions. Now, Hannah herself agrees. It is as yet impossible to see and measure to what extent these particles utilize 4D, quote-unquote, hidden tunnels under natural and unmanipulated circumstances.
I completely agree, and I don't think the electrical circuit was ever intended as a be-all and end-all. So his concern is completely accurate. There are other ways of getting these extra dimensions which are much more faithful to properties that you would expect from a dimension and that are much more likely to have this sense of like the right kinds of interactions.
A lot of the physics that we are interested in for this so-called dimension hopping don't have anything to do with particle interactions at all. Now, there's a whole other branch of materials physics that have to do with interacting materials and how do you define topological materials when interactions are not merely present but strong. That is a subject of interest in itself. These things actually have real-world possible technological applications.
Already, other groups are taking on the mantle. A 4D quantum Hall experiment in Paris, for example, has been able to observe the motion of a particle in a 4D environment, opening the door to understanding the fine structure of these dimensions and studying interacting physics. And this is one of the really exciting futures for Price, Yadong, and others' higher dimensional research. Not only do we expand our physical knowledge about the nature of reality, possibly even proving the existence of a fourth or more dimensions, but it also has real-world technological impacts too.
There's a very common misconception that quantum physics is only relevant for studying microscopic objects, or really the properties of atoms, and doesn't really affect our daily lives. The normal computers that you are, watching this video on, for example, are powered by the laws of quantum mechanics.
Like all topological states, these materials have useful characteristics. It turns out that any impurities on the surface won't impede an electron's progress because it can always skip through a higher dimension. This makes them good electrical conductors. In the future, these exotic properties may not only accelerate current technology, but also power the next generation of super-fast quantum computers and beyond.
What I would hope is that some of these really fundamental questions that we've been asking about higher dimensions translates into, okay, this is an alternative way to come up with cool devices, to come up with cool ideas for controlling light and particles in the future.
And this, in the end, might be the most exciting part. Space portals and all-powerful mystical objects like Marvel's Tesseract or Interstellar's wormholes will likely remain relegated to the realm of science fiction. But here in the real world, as we embrace and explore a new and potentially more exotic understanding of our universe, the only limit is our ability to open our minds, to imagine, and to innovate. Could we be living in our own flatland? Well, now we may have the tools to answer that question. To dive deeper into the biggest questions ahead, like whether gravity is quantum and where all the missing matter in our universe is, check out our other video where 5 of the world's top physicists break down the next century of quantum breakthroughs.